Let's take a look at phase change in thermal energy. Remember, thermal energy is the energy of the particles that make up matter. And there's basically three phases or states of matter, right? Phases is another term for states. Generally, if we're talking about phases of matter, we're only talking about one kind of matter. But regardless, you can have liquid, solid, and gas. Okay? And I guess maybe it makes more sense to say solid, liquid, gas. These are our three common phases. Okay? And of course, solids have arranged particles that can't move out of position. They're all stacked up, and this is a crystal structure. And the reason they have this crystal structure is there are intermolecular or interparticle forces that hold these things together. Okay? Particles with stronger, or substances, I guess, with stronger intermolecular forces are going to tend to have higher melting points. They're going to stay solid longer. It takes more energy to get them apart. Liquids, of course, look similar but different. Okay, similar in that the particles are still close together, but different in that the particles are not ordered. There are no longer huge forces of attraction holding the particles together, or the forces have been broken down. The particles have gained enough energy to be in this stable crystal structure, to be in this loose structure where they can still slide around but are close to each other. And then finally there's gases, where the particles are few and far between and moving very, very rapidly. And we can basically ignore any forces of attraction between the particles in a gas. Okay? So solid, liquids, and gases are like that. Now the crazy thing about this is every substance has a melting point, and it's the exact, well, most substances have a melting point and a freezing point that are the same thing. Sometimes they're not. But usually melting and freezing occur at the same temperature. Okay? And the same with condensation and vaporization, right? Those being the phase changes that occur between solids and liquids and gases. And so vaporization and condensation also have a common temperature. Okay, and you guys are familiar with this. For water, it's 0 degrees Celsius and 100 degrees Celsius by definition, right? At 0 degrees you can have liquid water, and at 0 degrees you can have solid water. We call solid water ice. At 100 degrees Celsius you can have liquid water, but you can also have vaporized water. Okay? And so what's the difference? What's the difference between this arrangement and this arrangement, between solid and liquid, or between liquid and gas? The difference is particle arrangement, not necessarily particle speed. Now, the lab we did on Friday involved measuring the temperature of water as we added energy to it or subtracted energy from it, depends on how you want to look at it. Okay, but basically what we did was we said, okay, we have a calorimeter with some warm water in it. Okay, so our temperature in the calorimeter started up here, nice warm water, and we added some ice cubes, and we stirred and stirred and added some ice cubes, and stirred and stirred and added some ice cubes until all the ice cubes had melted and the water had gotten fairly cold, and then the temperature started to come back up, right? It started to take in energy from the surroundings. Now, what we did was we measured the temperature before and after we added ice. So this was 0 degrees Celsius. This was around, I don't know, 70 degrees Celsius. And we had an initial temperature right here and a final temperature right here. Now, what happened was the ice melted. Okay? The ice melted. Now, what caused the ice to melt? Well, the ice absorbed energy. Okay? And we can see that because the water in the calorimeter, which is what we were actually measuring the temperature of, got cooler, right? Its temperature went down. And so this means that the water lost energy, the ice melted, it absorbed energy. Okay? But we stopped measuring the temperature as soon as the ice all melted. Okay? We didn't want to measure how much energy it took to warm ice up to 0 degrees, and we didn't want to measure how much energy it takes to cool ice or to warm water up past 0 degrees. What we wanted to do was measure how much energy it took to melt ice. So we started with ice that was already a little bit melty. It was already at 0 degrees. It was starting to change, and we ended when the ice all melted. And we have this cool temperature curve, and from this we were able to calculate Q, the amount of energy released by the water and absorbed by the ice, and relate that to how much ice melted. Okay? And what we found actually we had some really good results, is that it takes quite a bit of energy to melt ice. Okay? And if you guys have ever paid attention to ponds as winter ends, as the ice starts to come off of them, it takes quite a few warm days in a row to get the ice to come off a pond. And same at the beginning of winter, it takes a while before water freezes. There's a lot of energy trapped in a phase change. Okay? And the energy trapped in a phase change is what's called the heat of fusion or the heat of vaporization. Okay, so let's define that. Heat of fusion. Okay, heat, remember, is the transfer of thermal energy. So heat of fusion is this is the energy trapped in a phase change, but this is a specific one. So this is the energy released when a liquid freezes. Now I want you to think about that. Okay, when a liquid freezes, it's got to go from unordered particles to ordered particles, and that's releasing some energy. It's releasing whatever energy it took to melt it in the first place. So generally we think of freezing as getting colder, and while the substance might get colder after it freezes, before it can freeze, it has to lose its energy. So this is the energy released when a liquid freezes, or the energy gained, energy absorbed, I suppose, energy absorbed when it melts. Okay, now every substance has its own unique heat of fusion, just like every substance has its own unique specific heat. For water, for ice anyways, the heat of fusion is given in as 334 joules per gram. Okay, it's called QH or HF, I suppose. I'll use the book's notation. Okay, the heat of fusion for water, the heat of fusion for water is 334 joules per gram. You'll notice this is not joules per gram degree Celsius. Okay, remember our lab where we actually froze water and melted water. We had 0 degrees Celsius, and we had this one curve freezing. It started up here, we put it in the salt water, and it kind of hung out, did this thing here, and then it got colder. And then we reversed the process. We started cold, and it kind of came up to here, and then it got warmer. Right here, this thing right here, this is our phase change. This is melting and freezing. There is no temperature change here. Instead, the particles are rearranging. They're going from disordered to ordered or ordered to disordered. Okay, and energy is involved in that. It's not involved in kinetic energy. It's not involved in temperature. It's not involved in particle motion. It's involved in particle arrangement. So this heat of fusion, this 334 joules per gram, this is how much energy, 334 joules, it takes to melt 1 gram of ice. Okay, so we have to be careful when we have a phase change involved with something, because even though there's no temperature change, there is still an energy change. And so we think of Q equals mc delta T. That's fine as long as there's only one state. Okay, one state. If there's 2 or more states or 2 or more phases, then we have to deal with that. Okay, of course, just like there's heat of fusion, there is heat of vaporization, and it's exactly the same thing, except it's the next stage, right? If we were continue to add heat to this, it'd get up to boiling point and then do the same thing. Right here, another phase change. So heat of vaporization is just like heat of fusion, only it's for vaporizing. So this is the energy gained or lost when something condenses or boils away. Now, I want to do a quick example problem for you of how you can deal with this. Okay, how much heat is absorbed by 100 grams of ice at negative 20 degrees Celsius to become water at 0 degrees Celsius? Now, let's do a more complex example than that, right? Let's start hard, and then anything will be different. Anything else will be easy. So, the example problem the book uses, it says 1.5 kilograms of snow at let's say minus 20. We'll go with that. At minus 20 degrees Celsius is heated to make 1.5 kilograms of water at 70 degrees Celsius. Okay? How much energy is required? Okay, now you have to be very, very careful with this. There's a lot going on. You have to divide up your problem, okay? Because snow is solid water. It's ice. It's frozen. It's below the freezing point. But as soon as it gets to 0 degrees, it's going to absorb some more energy to turn to a water, and then it's going to gain more. So we can't just use the Q equals mc delta T equation. Okay, this is only for one phase. We have to use this for each phase plus whatever heat of fusion happens. Okay, so remember, start with what you know. Okay, we know we start with a solid. The solid has to melt, and once it melts, it becomes a liquid. Okay, and we can go ahead and list everything I know about it. The solid has a mass of 1.5 kilograms. Okay, when it melts, there's still 1.5 kilograms of it. As a liquid, it remains 1.5 kilograms. We're not gaining or losing any particles. The specific heat, okay, now you've got to be careful. The specific heat of ice is not the same as the specific heat of water. Since the particles are in a different arrangement, a different structure, it does have a slightly different specific heat than the specific heat of water, liquid water. Okay, so ice has a specific heat of 2.06 joules per gram. It melts. There is no specific heat for melting. Okay, what we have is a heat of fusion, and the heat of fusion for water that is listed in a table on page 324 in your book is 334 joules per gram. Okay, and then finally we have liquid water, and the specific heat for liquid water is 4.18 joules per gram degree Celsius. Ooh, I forgot my unit here. 2.06 joules per gram degree Celsius. Now, okay, there's one more thing we got to go through. It's our delta T. Okay, delta T equals, here it's going to go from negative 20 to 0 because 0 is its melting point. So this is 20 degrees. Here this is a change of 0 degrees. Okay, it doesn't change temperature as it melts. That's why we get the flat line. And here our delta T is 70 degrees. It's got to go from 0 degrees all the way up to 70 degrees. So what we do is we figure out how much heat it takes to warm up the ice. Then we see how much heat it takes to melt the ice. Then we see how much heat it takes to warm up the water. We add it all up and we get our answer, right? So it's still Q equals mc delta T here, but it's 1.8 m. Oh, that's kilograms. So I'm going to put all these in joules. That's 1.5. Sorry. I'm going to put all these units either in. My units have to match. So either I have to go grams or I have to use joules per kilogram. Okay. I'll probably use joules per kilogram here. So I'll use 1.5 kilograms times 2060, right? Move my decimal place over 3 times and get kilograms. 2060 joules per kilogram times 20 degrees plus heat of vaporization, 1.5 times 334,000. Again, I'm moving my decimal place over 3 times because it's joules per kilogram, not joules per gram. And then plus 1.5 times 4180 times 70 degrees. Okay, now this is going to be a lot of energy. I'm not actually going to work this problem out for you, but you see the idea. Okay, when you have a phase change, you have to deal with the heat of fusion. If it had been liquid to gas, then you've got to deal with the heat of vaporization. Okay, but it is a process where you have to deal with the energy involved in a phase change.